Well, good morning. This is 8:10 actually on Monday morning, the 3rd of April 2017, first day back after spring break, but unfortunately I'm the only one back after spring break. My computer hardly would come back. It took forever to boot off this morning and get PowerPoint to load and Screencast-O-Matic, but we're finally here, but no students are here, so we'll go on and get started. It's supposed to be Math 237 linear algebra, so hopefully some of you will be hearing it. Hopefully some people will be coming in. So we'll begin at current slide and go from there. Okay. See if I can get the pen activated here. Yeah. Okay. We left off last time, long time passing. By the way, let me get today's class set up. Today is the 3rd, like I said. Do have a couple of announcements to make that pertain to what's going on this week, especially with my office hours. Unfortunately, I hate it that it's the first week after spring break and this is happening so soon, but I found out over spring break that they have scheduled me a doctor's appointment for tomorrow. I think it's 11:20 or 11:40, something like that. So that means that my office hours, which are usually 10:45 until 1:15 on Tuesdays, I will not be here at 10:45. I'll probably miss most, if not all, of my 9:30 class because I have to be there for lab work before the doctor's appointment, and then the doctor's appointment will last probably the better part of an hour as well. It shouldn't, but late appointments like that sometimes get backed up, and I won't be in with the doctor an hour, but it will be I'll probably be away at least an hour, but I will be back. I'll have my 8 o'clock class tomorrow morning and may start the 9:30. I haven't figured out yet. Got to verify the time of the appointment. That came in early in spring break, and I don't have it right with me now what the appointment is. Now, that's one thing. Then Friday, I have an infusion. So normally my office hours on Fridays on the Birmingham campus is 7:45 to 1 o'clock. I will be out the entire time because the new drug they have me on, the infusions basically take all day. So I will be there 8 o'clock, if not earlier, and then we'll, of course, to be there 8, I have to get parked by 7:45, and if they need blood work again, which I hope they won't because I'll just have had it on Tuesday, hopefully I won't have to do blood work again for an appointment on Friday. So I'm hoping not to have to be there that much earlier, but I will be there at least by 7:45. But then the new drug I'm on, basically that's all day long. There's lots of things they do beforehand and then during and slow down, and it's a long process. So anyway, I won't be on campus at all on Friday. Those are the two announcements I know about, so let's get on with the class. The last thing we did, we started in Chapter 3, Determinants, 3.3 Properties of Determinants, and the first of these that maybe the second of these we talked about, was a determinant of a matrix product. Theorem 3.5 on page 120. We did this, we talked about it. If A and B are square matrices of order n, they've got to be square in order to talk about determinants. They've got to be, if they're square, they've got to be the same size, order n by n matrices. Then the determinant of a product of two matrices, square matrices, same size, is the product of their determinants. Now, that was at the bottom of page 120. At the top of 121, where we start today, this can be generalized to conclude that if you have any, and this time, this is sort of the middle of the proof of that. You know, remember when we were doing elementary matrices, and this is what the proof's all about, you can they start with, if E is any old elementary matrix, then by theorem 3.3, which is back in the last section, I believe it was, the next three statements are true. If you obtain E from I by interchanging two rows, then the determinant of E is -1. We did this before. If you obtain E by multiplying row I by non-zero constant C, then the determinant of E is C. These are elementary matrices, remember. And if you obtain E by adding a multiple of one row to another row, then the determinant of E is 1, okay? Because elementary matrix, its determinant is going to be 1. All right. Additionally, by theorem 212, this is back in the previous chapter, if E results from performing an elementary row operation on I, the same elementary row operation is performed on B, then the matrix EB, results. That's a strange sentence. And it follows that the determinant of EB is the determinant of E times the determinant of B. Okay? Now, they go on and say that can be generalized to conclude that if you did all the elementary matrices, E1 through EK, multiply them by B in order, okay, take the determinant of that product, then that would be the determinant of E sub k times the determinant of E sub k minus 1 times the determinant of E sub k minus 2, and on down to E sub 2 times E determinant of E sub 2 times the determinant of E sub 1 times the determinant of B, where EI is an elementary matrix. Now consider the matrix AB. If A is non-singular, which would have to be if you're going to take a determinant of it, okay, non-singular matrix, then by theorem 214, the one we're talking about, well, a couple later in the last chapter, it can be written as a product of elementary matrices. How many ever row reduction steps you need to take. So that would be E sub k times E sub k minus 1 times E sub k minus 2 times ... down to E sub 3 times E sub 2 times E sub 1. Okay? And then the determinant of AB would then be the determinant of all those elementary matrices that made up A multiplied together times B, and that would be the determinant of E sub k. You know, break those down into individuals, you know, again, and then you wind up with the determinant of A times the determinant of B. Now, again, that seems like a very circular kind of a proof. And in some sense that it is, but don't let it freak you out or anything. It's just a proof. Now, the next theorem shows a relationship between the determinant of A and the determinant of CA, okay, where C is some constant multiplied by the matrix A, okay? And here's what it says. If A is a square matrix, and I apologize if my writing's a little bizarre today. I'm doing work over the spring break week. The latter part of last week we were earlier I had gone up and taken a lot of briars out of a row of hollies and out of some other dogwood trees and other things up at the lake, our lake place, and big, long briars. And then that was a month or so ago. And over the spring break week, we were burning some of that. So I was having to handle that stuff again, and a couple of the thorns went right through the gloves and stuck me, and a few of those actually got stuck in me. So I had some splinters that I haven't been able to get out until recently, but my fingers are still very sore, and that's why it's sort of hard writing it. Of course, they're on my left hand, which is the one I write with. So if A is a square matrix of order n, okay, C is a scalar, okay, then the determinant of CA is equal to C to the n times the determinant of A. I don't like using DET, that's what the book uses. I just like doing the bars, okay? Look like absolute value bars, but in matrices they mean determinant of the matrix, okay? Now, I don't know if your first gut reaction would have been just pull the C out, because if you're doing scalar multiplication, well, if that would have been your reaction, that would work if you were just doing CA, that's equal to, if you're multiplying C times A, that's just C times the matrix that's A. But if you think about it, what does that mean? C times the matrix that's A. Well, if A was A11, A12, A13, again, my writing stinks, all the way up to A1N, A21, A22, A23, up to A2N, A31, A32, A33, up to A3N, and then this on down to A sub N1, A sub N2, A sub N3, down to A N N. If you were to multiply that C by that matrix A, however big or small that A was, what you're going to do, you're going to multiply every element in that matrix by that scalar C. Okay? Then if you think about doing the determinant of that, of course, then every one of these is going to have a C in it. If you multiply this through, that's what you get. C's in front of every one of those, okay? Every one of those, okay? Now, if you do the determinant, that would be CA times the determinant of this. If you do the CA11, times the determinant of the inner one, okay? Well, what's the determinant of the inner one? That's C 22 times, I'm going to take the simplest way of doing it, times this. So it would be C A11 times C A22, okay, times C A33. If you just take them down and every one, you just do the next smaller minor, and just go down the main diagonal, you would have this. So it would be times C times the entry A, well, actually it goes up to NN, okay? If you think about it, that's what you're doing. You're going down the diagonal. If you just take the simplest one, you're not looking for the easiest way, you're just looking for the most straightforward way to do those determinants, you would just do that. Well, whatever you got, you've got 1, 2, 3, 4, n of those c's, so that would give you c to the n times the determinant of a. And that's exactly what you get there. Okay. It gives you another way to approach it, but look at that too, see which way you like better. All right, so what do we do with this? Let's try example 2. Okay. Example 2, here is your matrix A. Find the determinant of this matrix, a good old 3 by 3. 10, negative 20, 40. Hey, good to see you. I was beginning to worry, to think I was going to talk to myself the whole time. Okay. I believe today's the 3rd, right? Okay. All right. And by the way, thank you. By the way, I have your letter done on my flash drive, but I wasn't doing the printer all week, so I'll print it off probably between 3 and 5 today. I'll have it for you. You need to turn it in, or I need to turn it in? Okay. All right. Well, I'll give it to you Wednesday then. Okay. Is that okay? Yeah. All right. Because it's not due till the 15th, right, or someday after that? 16th. Huh? April 16th. 16th. Okay. Well, not because we'll try to get it to you on by Wednesday. Like I said, I'll try to print it out today. If I'd have gotten, could have gotten.
I'll be here. I take physics 214.
Uh huh.
I'll be here.
Oh, okay. Okay. Well, why don't you come by my office? Well, let's see. I'm in class until 3:15, so I won't have it printed then. But if I can get it printed in that next 15 minutes, I'll do that and get it up to you. Y'all have a guest speaker or anything today? Okay. Do you sit right there? Okay. I thought you did. You always have. So what I'll do, when I get it printed, I'll bring it up and just bring it in the back of the class and give it to you, because I doubt if I'll get it printed before that, because all right, we're on page 121 in chapter 3, section 3.3. Yeah. Yeah. Okay. By the way, put this out. Stiff and sore. I don't have any students here. I'm just sitting there. I don't move around as much. Okay. What was your question? Number 2. Well, this is second test or first test? I thought you had already turned in the first test. Okay, I've just got to find it. Test 2, here it is. Okay, how many of these do I have? Okay. Which one? Number 2. Oh. Okay. If you recall, there's 3 properties of determinants. Is this the test? Okay. Did I just give it to you early? Because we're not through with the determinant chapter yet. I'm trying to figure out. Yeah. Okay, is it on determinants? No, okay, I've got the wrong test too. Okay, that's my problem. Yeah. Yeah, okay. You see, the last time I taught this course, I didn't do a separate test for chapter 1, so my test 2 was then chapter 3. Okay. What is the question?
system, then displacement from AX to B.
Okay. Ah, here we got it. Yeah. Okay. Okay. I just hadn't dug down deep enough. Here we go. Well, actually, I ain't going too deep. So number 2, write the system of linear equations in the form of AX equal B, then use Gaussian elimination to solve the matrix equation for X. Okay. Now, A is a matrix, right? X is a column vector, and since this is a 2 by 2, it's x1, x2. Okay? And then your solution vector is in the vector that's after the equal sign. The column vector is after the equal sign. Okay? So basically, do the coefficient matrix times your, let's see if I can find an example in the text that's similar to that. I'm pretty sure I can. This is fairly early in chapter 2. Okay, it's a lot like your homework exercises on page 49, numbers 41 through 47. It's like example 7. Oh, wait a minute. No, more like example 6. Okay. Example 6 goes the other way. Well, actually, the thing right before example 6. You see, top of page 45. Okay. There's a matrix just like this one. That's a 3 by 3. This is a 2 by 2, so this is even easier. You write down the matrix A, which are the coefficients. You write down the column vector X, which this only has 2 elements, not 3. And then you write down equal, and then the column vector B, which is only 2 elements. Does that make sense? Okay. All right. How about you pick on page 49 any of the problems 41 to 48. I don't care if it's even or odd. Pick one up. Yeah, any one of them. Which one? 41. Okay. I'm sorry, I can't hear. So this is on page 49. Okay. This is 2.1 exercise. And number 41, you said, right? Okay. It says, write the system of equations. Here it is. Minus x1 plus x2 is equal to 4. And minus 2x1 plus x2 is equal to 0. Okay? There's your system of equations. Okay? It says write that in the form of AX equal B. Okay? Now, what do you reckon the A would be? The coefficient matrix, which would be negative 1, 1, negative 2, 1. Okay? What's your column vector that represents the variable x? Two components, huh? No, that's your b. It's 4 and 0. The column vector x, oh, he is back from spring break. Okay. All right, good to see you. It's what? X1 and X2. There it is. Okay? Now, and it says solve that matrix equation for X. And the homework actually says do it with Gauss elimination. Okay? So you could do it by inverse matrices, but we hadn't done this at this point, so do it by Gauss elimination. In that case, you would take your coefficient matrix, minus 1, 1, and then augment it with the 4, and minus 2, 1, augment it with 0, and do your Gauss elimination. What would be the first thing you would do? Yeah, so multiply the top row, minus row 1 becomes the new row 1, okay? So I'm going to do it real easy. Watch me. Plus, minus, minus. Okay, did it. What's the next thing you would do? Second? Okay, and how would you get it? 2 plus row 2. And that becomes a new row 2. Okay? So you leave the top one alone. 1 minus 4, the one that you changed. Okay? And then what we're doing, we're working an example back from 2.1, number 41, page 49. It's similar to the question 2 on your test. Okay. Huh? Oh, you did? Okay. Do you follow what we've done so far? Okay. Now, do that operation we just talked about. 0. What do you say? Okay, 2 times negative 1 is 2 times negative 1 is plus 1. Negative 1. Okay. Negative 1. Okay. And second? Negative 8. Okay. All right. So that's the next step. Okay. It says then use Gaussian elimination. It doesn't say Gauss-Jordan elimination. I don't care which one you use. We're just going to use Gaussian elimination. What's the last thing we need to do to get at Gaussian elimination? Yeah. Negative row 3 becomes the new row 3. So that's going to be plus, plus, right? All right. Now, what does that tell you? This is the coefficient for x2. So this tells you x2 is equal to 8. Okay? And what does it tell you x1 is? Well, the top row says that x1 minus x2 is equal to negative 4. Isn't that what it says? Okay, this is the coefficient for x1, there's the coefficient for x2. So it's x1 minus x2 is equal to, now we've adjusted this and it's become negative 4. But we know what x2 is, right? What is it? x1 minus 8 is equal to minus 4. And what do? Add 8 to both sides. And that gives you x1 is equal to 4. Well, let's see if that works. Okay. Minus 4 plus 8, sure enough, is 4. Right? And negative 2 times 4 is negative 8 plus 8 is 0. Yes, that is our solution. So when it says find what x is, then you write it this way. The column vector x is 4, 8. Right? All right. Does that answer your question? So the first big blank is basically to write something like this. Write matrix times column vector of the variable equal the column vector of the solution. Okay? And then the next part says solve it with Gauss elimination. And let me you see the blank blank there? Those are supposed to be connected, but in the word processing package that I was using, it didn't connect them. So that really is one blank up and one blank down. It is only 2 numbers, just like you have here. But the word processing package, the equation mode, doesn't do a solid line there. They don't connect, but they should connect. Okay. The last time I had made out this test, I put just a single line there, and the students had trouble writing small enough to get it in there, so I put bigger lines there, but they didn't connect. So that's just, those are the 2 little blanks there should be connected to one line. Number 5? Okay. And again, the same thing with the x at the bottom. That's going to be just one solid blank, another solid blank. Okay? They got 2 little blanks, but they just wouldn't connect. Okay? Well, that probably is yeah, that's in the next section, I think, where we do inverse of matrices. In fact, it may be in 2.3. I believe it's 2.3. Yeah, 2.3. Okay. This is very similar to skip right over it. Oh, well, oh, here it is. It's example 8 on page 70. Okay. Now, they do Gauss-Jordan, but what they're really looking for you to do, and this would be like homework exercises on page 72, use an inverse matrix to solve each system of linear equations. Okay, or this is a matrix equation. Let's see if we can find one that actually words it like that. I don't see it, but this is just one step away from that. Okay? All right. So you pick any one of 45 to 48. Which one? 45. Okay, there's A, B. You want both of them or just one? A, okay. So, actually this is one more step than the one that we're going to do. I just can't see one that's just like the one we're going to do, but it's just one step more, okay? So, this is page 72. This is 2.3 exercise. And by the way, y'all came in after I said it on the thing. My writing seems a little worse than usual, which is hard to believe. It's because I was doing some work over the weekend, and we were burning some brush, and there were a bunch that had thorns on them, you know, and I got a thorn in my finger. I could not get that thing out until actually this morning. I finally got it out, but my finger is so sore. It's on my left hand, of course, so it's hard to hold the pen without pain. But anyway, I'll manage. Okay, 2.3 exercises, and this is number 45A, you said, right? Okay. Here's what we're going to start with. X plus 2y is equal to -1, and x minus 2y is equal to 3. Now, in reality, it would be so simple just to solve this right like it is, without doing any determinants or anything else. I mean, without doing any matrices or anything else. But you give me the matrix equation that stands for that. Okay, 1, 2. Oh, no, the matrix equation. -2, xy is equal to -1, 3. Oops, I always have to stop myself from putting a line there. Okay. Now, that's basically where your number 5 picks up. It gives you the matrix, the variable vector, and it gives you the constant vector, right? It says solve this using an inverse matrix. So guess what the first thing we got to do? Inverse matrix for that matrix we have there. Now, this being a 2 by 2, that's a pretty easy thing to do. How would you do it? Okay, you do the determinant. Okay, and what would that give you? -2. 2 minus 2 is -4. Okay, what do we do with that? 1 over, or -1/4, times, and then what matrix do we put there? Say again? Okay, what you do is reverse the diagonal, right? That becomes -2, 1, right? And then you negate the off diagonal. Is that right? Oh, -1. Okay. Let me make sure I'm telling you right, because we did that. Yeah, you reversed if you go back to page 66, right about the middle of the page, A inverse where A is A, B, C, D, A inverse. This only works for 2 by 2s now, and this is a 2 by 2. It's 1 over the determinant, which we've already done, times, you reverse the main diagonal, put the -2 on top and the 1 in the bottom, and then you negate, but leave them where they were, the off diagonals, and that makes it a -2 minus 1 on the off diagonal. You see that? Okay. So there's your inverse matrix. Okay? Yeah. Now, I'm real tempted to multiply the -1/4 through, but that's going to give me a bunch of fractions. Okay? I like to put those off as long as possible. I know you love your fractions. But what we're going to do then is going back to example 8, and what you do then, your solution is your xy is equal to, and this was from theorem 211 at the top of the page, is this inverse matrix, which I'm going to put as -1/4 times minus, you know what else I'm going to do? I don't like all those minus signs. So you know what I'm going to do? I'm going to make that a plus, that a plus, that a plus, that a plus, and that a minus. So I switch 4 minuses and 1 plus to 4 pluses and 1 minus. So make that a plus, and that'll be 2, 2, 1, -1. Okay? And then multiply that by our b vector, which you see is what? -1, 3. Okay. Now I'm being real lazy about leaving that 1/4 out by itself, because it's just a scalar. I can multiply anytime I want to. Let's do the matrix multiplication of the other part. It's 1/4. I already dealt with the minus sign. So what would you have here? Can you even multiply those two? And what will you get? What size will you get? 2 by 1, exactly. There you have it, okay? I did one a little blank here, okay. Now, you tell me how to fill in that. Do your multiplication. First entry is the 1, 1 entry. So you do first row, first column, right? What does that give you? Oh, spring break was really long, wasn't it? First row by first column. 4. Okay, very good. Feel like a dentist. Okay, next. -1. Second is -1. -3 is -4. Okay, I thought you said 2. Sorry. Okay. Now I'll multiply by 1/4, and what do I get? -1. All right, let's see if that works. Okay. Go back here and put in for my x. See, this thing is equal to this thing. So the x is 1. 1 plus 2 times a -1. 2 times, is -1. That checks. And then the second one, I do a 1 minus 2 times -1, 3. Yeah, it works. There's your solution. See how it works? First, find the inverse. 2 by 2s are easy, okay? 3 by 3s are a little more difficult, and after that, they get even worse, okay? But find the inverse, and then your solution matrix is going to be the inverse of A times your the variable matrix will be the inverse of A times the solution matrix vector. Do the multiplication, and you've got what xy is. And the last part was just checking. Does that make sense? Okay. Now, in reality, what would I have done with this problem? Add the two equations together, right? That gives me 2x, eliminates the y, is equal to 2. X is equal to 1. Then plug back into any one of them. Remember? 1 plus 2y is equal to -1. Subtract 1 from both sides, and you get 2y is equal to -2. Y is equal to -1. It was so easy to do it that way, but they wanted you to do it this way. Okay? This is a pretty good check. If you had okay, now, is doing an inverse the easy way to do a problem? Generally not. Okay, Gauss-Jordan elimination usually much easier than doing this. However, if you had a whole bunch of them, like that example had there, that you had 3 that had the same coefficient matrix, you're just changing your solution vector, then, yeah, do your inverse once, and then multiply that same inverse times your solution, different solution vectors, you come up. In that case, it's easier. And that's why your homework exercises there, what was it, 45 through 48, they had 2 of them with identical coefficient matrices. If you got 2 of them to do, it might be easier to do it that way rather than one of the other methods. 2 by 2s is still so easy to do it the other way, but that was just for practice. Any other questions? Good questions?
Yeah,
Number 7. Number 7. This would be very similar to homework exercises. I'm emphasizing homework exercises. Let's see. Was similar to one 55 and 56. That's finding singular. Here you're finding non-singular. I even can't believe that's what they asked for. Did I even type that right? Let's see if I can find my original. Yep, I guess I did. Okay. What does it mean to be non-singular? Well, let me clear the ink. This will be page 72 again. And which one you want to do? 55, 56? I don't care. Which one? 55. Page 72. Same thing as before, only now it's 55. Okay? And I'm going to change it. It says Find X such that the matrix is not singular but non-singular. Okay? And this will be 4x, -2, -3. Now, tell me what it means to be singular or non-singular. I don't care which you do. Just tell me which one you're defining.
Singular is invertible.
What's that?
Singular is invertible.
Okay, if it's singular, it's non-invertible. Non-singular would be invertible. That's correct. How about something else? There's several things that are all equivalent. Okay? If you go back, well, I thought it was in this. Maybe not. What's that? Okay, I still couldn't hear what you said.
I said example 4.
Example 4. Yeah. Okay. 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 Go down, especially since this is 2 by 2, right? Go down the middle of the page there about that determinant. And what does it say there? A is, which also means, second, yeah, if and only if the determinant is not equal to 0. But what does invertible mean? In terms of our question here? Okay, no. Invertible means there is an inverse. Okay, but in terms of number 7 question, singular or non-singular? If it's invertible, it is which of those terms applies to invertible? Non-singular, exactly. Okay? Now, okay? So this says find X such that the matrix is invertible. That means the same as non-singular, right? And what has to be true if it's non-singular or invertible? The determinant is not equal to 0. So all we have to do is get the determinant. And what is the determinant of this matrix? -12. Second. Except you do the minus of that. 2x, yeah. -12 plus 2x cannot equal 0, right? That makes it invertible or non-singular, right? Okay, can you solve the inequality? Second, add 12 to both sides. And what do you get? 2x is not equal to 12. Divide both sides by 2, and that gives you x is not equal to 6. Okay? And notice your answer here. Hint, hint, I wrote it as x is not equal to. Does that make sense? Okay. You just ran over somebody. No, never mind. I probably can, but I'm not. Did we? Oh, number 6. Okay, I thought we just did 7. Okay. Now, it says find A from that piece of information. Okay? Now, that looks a lot like theorem 2.8, doesn't it? Number 3. Theorem 2.8, number 3, top of page 67. Let's see if they have any exercises like that. Oh, there we have one. Any one of 41 through 44, the C part. Which one?
B. B of 41.
41? Okay, 41. The A one, I mean, we're doing the C part of 41 because that's just like this one, right? Okay, and we don't need the B because there's no B in it, so we'll just use this. Oh, that's not quite the same, is it? Let's wait, flip over one more page. Nah. Yuck. This was, the one they gave you here was a little too simple, I would say. But let's do 41 and we'll just make it up. Okay? Not quite the same. But we'll just change it appropriately. So this is page 71. Same, everything else as before. 71, number 41, C. I'll put modified. Okay. Here we have 2a to the minus 1 is equal to, this time we're not going to say a to the minus 1, we're going to say is equal to 2, 5, negative 7, 6. Now this isn't the same as the one in the book, but it's similar to it. Okay? Now, if you flip back to see your theorem 2.8, number 3, what do you notice there? What is CA to the minus 1? What does it tell you it is? 1 over C, and in this case, 1 over 2 to the times A inverse. So the one in the book was really, really easy. You just plug in A inverse there. Okay? But what we have here, that this is equal to 2, 5, negative 7, 6. Okay? Now, what are we going to do to deal with that? What would you do? And the question is find A. So what would you do? Multiply 2 times both of these, right? That'll wipe out your 1/2. That gives you A inverse is equal to what? Now, yeah, let's go on and do it. 4, 10, negative 14, 12. All right. Now we got to find A. Now, how do you do that? How do you do it? find the determinant. Okay, and what's its determinant? For some reason my pen disappeared. There, no? Yeah, there it is. What's the determinant? Is 48. Plus 140, isn't it? Right? Big number. And that is 188. Is that right? Okay. Big number. Okay. All right. That's the determinant. Well, what do we do with that? 1 over 188 times, say again? Wait. Negate the off diagonals, reverse the main diagonal. So you flip these two. No, you don't negate it. Flip them. 12 and 4. Just flip those two. Then you negate. And what do you get? Negative 10, positive 14. Okay. Now, one thing I do right off the top, and this is why I was hesitating before, but since you said it, we went on and did it. I would factor out a 2 because a 2 comes out of every one of those terms there. So the 2 out of this, 2 will go into that 1 over 94, right? Okay, half of that. And this would be 6 minus 5, 7, 2. Okay? Now, it's perfectly okay for you to leave it like that. That would now be A, the matrix A, because it's the inverse of its inverse. If you wanted to write it in fractional form, which I know Nigel does, that would be 6 over 94, which would be 3 over 47. 7 over 94. Will that go at all? So 7 over 94. And 5, I know that won't, minus 5 over 94. And that last one would be 1 over 47. You could write it like that, but the other way is just as good in my mind. Okay? See how that works? Any other questions? Huh? Number 9. Okay. Well, I find having to find all these homework exercises, it seems like that should be what you're asking. Don't ask me what number 9 is. Ask me to work one like number 9. But, okay. Number 9. Find a sequence of elementary matrices whose product is a given non-singular matrix. Okay? Well, elementary matrices was 2.4. And this will be similar to example 4, I believe. Okay, which would be, let's see if I can find one. Find the sequence of elementary matrices whose product is the given non-singular matrix. would be, yeah, like 27 through 34. Pick one on page 82.
$29.
29, okay? So this is page 82. All right. 2.4 exercise. And number, which one you said? 29? Okay. Find the sequence of elementary matrices whose product is the given non-singular matrix. So here's the given non-singular matrix. 4 minus 1, 3 minus 1. And you know, I'm a cynic, so I always check to make sure it is non-singular. Is it? How would you check that? Say again? Determinant. And what would that be? Say again? -4 plus 3 is -1. That's not 0, so that is a non-singular matrix. That's all you have to do for that. Okay? So, we know it's a non-singular matrix. They said it was, but I didn't believe them, so I want to make sure. And we want a sequence of elementary matrices whose product is this matrix. Okay? Now, again, if you go back to example 4, find the sequence of elementary matrices whose product is this one. Okay? What you do, okay, is start with this one and do your elementary row operations, but as you do them, come up with the elementary matrix that does the same one, but also come up with the inverse elementary matrix that does the same one, right? Okay. So Les, what would be your first operation here? Oh boy, you picked a good one, didn't you? What would you do first? Frankly, yeah. Gauss-Jordan elimination. You want it in reduced row echelon form. It's the first thing you want to happen. You want the upper left to be a 1. Now, you got two choices. Now, I don't really care which one you do. You can either go with what you got, or you can flip and then go with what you got. It doesn't really make a lot of difference. Okay, so what would be your first step then? Yeah. Row 1 divided by 4 is the new row 1, right? So that new matrix will be 1, -1/4, 3, -1. You didn't do anything to the second row, right? Now, we want to do the elementary row operation that does the same thing. Now, the elementary row operation, remember, you always start with the identity matrix, okay? Okay, identity matrix is 1, 0, 0, 1. Same size, right? Now, what would the corresponding identity elementary that you would have? No? Say again? You're doing row 1 divided by 4. Same operation, you do it here. That would be 1/4, 0, 0, 1. No, you only do it you didn't do anything to the second row. Okay. Now, that's your elementary row operation. We'll call that E1. We also want to know what E1 inverse is. Okay. Now, what would it be? Okay. Second. Okay, yeah, we're going to do that in a minute. Okay, what we want to do is the inverse, this is the elementary, okay. This is the first step we did to reduce it, right? But at the same time, or with that, we want to do the same operation to the identity matrix to do this elementary matrix. But at the same time, I want you to do the inverse for this elementary matrix. And what would that be? Not 1. Okay. Whatever. Okay. Now you're sort of doing backwards now. Whatever you do here, when you multiply this by that, you better get that, right? Okay, that's what the inverse does. Multiply a matrix by its inverse, you get the identity matrix. So what have you got to multiply this by to make that a 1? Well, 4, exactly. Okay. And the rest of them? 0, 0, 1. Right? Now let's try, see if it works. That would be 1 plus 0. That would be a 1. 0 plus 0, that would be a 0. 0 plus 0, that would be a 0. And 0 times 1. Yeah, that works. Okay? Now, go back to our matrix at hand. What's the next step we're going to do? Okay, so let's do it. We're not messing with this. 1 negative 1/4. 0. Okay. 3/4 is the first thing. You're right. Negative 3 times negative 1/4 is positive 3/4 plus negative 1. Positive 3/4 plus 4/4. Minus 4/4, I'm sorry. Positive 3/4 minus 4/4. Is that what 1 minus 1 is? Positive 3/4 minus 1, which is 4/4. Positive 3/4 minus 1. Is what? Negative 1/4, exactly. Negative 1/4. Okay. Well, what's the elementary matrix that does the same thing? This now operating on that. 1, 0, because you didn't change that first row at all. Say again? Negative 3. 1. Exactly. Now we need to do the inverse of that one. Okay? Any ideas? 1, 0 on top. Got it. Let's try that. Okay? Let's try. That's 1. Got it? Got it? Yes! Yeah, that works, doesn't it? Okay. So there's your inverse matrix there. What's the next thing we're going to do? Go back to your one here. You try to get this thing to be a 1. So what do we got to do? Negative 4, row 3. Yeah. Okay. So this is going to be 1, negative 1/4, 0, 1. Okay. Now we do that same thing to this one. And what do we get? 1, 0. Didn't change that. 0, negative 4. Okay. Now, what is going to be your inverse of that one? 1, 0. I'll buy that. How about negative 1/4? Let's try. Okay. 1 plus 0 is 1. Good. Is 0. Good. 0. That's good. Plus 1. Yes, that works. Okay. One last step. What's it? One-fourth, row 2. Where did I get a row 3? That's a row 2. Duh. Okay. 1/4 row 2 plus row 1. That'll work, won't it? Okay. What does that give you? Say again. 1. 1/4 is 0 plus 1 is 1. 1/4 of 1 is 1/4 plus minus 1/4 is going to be a 0. 1/4 of, oh, that's it. And then we 0, 1. That's exactly what we want. Okay? Let's do that to this one up here, and what do we have? One. Go! Did I do that right? 0, 1. Okay? What's going to be its inverse? Let me just check on something just for a moment here. Yeah, okay. All right, and what will this be? 1. Second. 4. Okay, let's see if that works. Okay, work, will it? Okay. I think what we need to do there is, yes. Well, I think it's negative 1/4, isn't it? We're running out of time. I'm sorry. Okay. Won't that work? Negative 1/4? Let's try that. 1, 0, that's 1. Negative 1/4 plus 1/4, that's 0. 0, 0, 0, 1. That works, right? Okay. We got that. Okay. Then we look at the last thing. We take these in order and we write them down. Okay. We do this one times that one times that one times that one. That series of elementary matrices. I lost my question here. Number 9. Find the sequence of elementary matrices. Now, this one wound up having 4. The one that you had, I think, doesn't have but 3. But if you need 4, put you an extra one out there. Okay? But you see what you got to do to get there. Okay? So what you should have are your inverse matrices in the order you did them. Okay? When you're doing the other, it's in reverse order. But when you're doing this one, it's in that order. Okay. All right. Actually, what we got accomplished today, it was actually before you came in. In fact, before either of you came in, we were just getting ready to do example 2. In fact, I'd written it down, but we didn't do it because he had a question. So that's all. Okay.